Good morning, class. I'm now going to address the question that I am sure you've been asking yourself. We've calculated the applied forces in terms of tension force, compression force, the moment and the shears. The question is, what's next after you've calculated all those applied forces? For this course, I've covered the applied shear forces and the moments. I'm gonna start with the moment. Let me start with the moment. Okay. There's a bending moment equation that we need to follow. Just like when we were taking moments, we've been saying that you must be within some certain rules. You must be guided by the rules of analysis. Here you've been guided by the rules of engineering bending equation. So I'm gonna start off with the bending stresses. Bending stresses. Why stresses? Remember, the forces are applied over a section, or in a section. So there's internal forces happening in the member itself due to the applied forces, like applied bending moment and applied shear forces. So I'm now starting with the bending. So there's an equation, the bending equation. That we need to look at. Stress over Y is equal to M over I and is equal to E all over R. Okay. E being the Young's modulus of that section, or the Young modulus for the section or for the material that you are designing. Like E, for example, for steel is 200,000 newtons per millimeter squared, or kilonewtons per millimeter squared, or it's newtons, MPa. Let me say MPa. That is E for steel. R is the radius of curvature. Remember, the beam is going to have a curvature under bending, R being that radius, the radius of curvature. M is the applied moment. I, second moment of area. Stress is the bending stress in this case. Y is either your Y upper or your Y lower. So how do you then use this formula? Guys, I must tell you, you don't use all three. You select maybe the first two depending on the information that is given to you. If you can get this and that information and you want to calculate the stress, you will take the first two terms of that equation. Or if you know that and these ones, for some reason you want to calculate E, or you want to calculate the radius of a equation, you can take the first two, or you can take the first and the last term of that equation. You don't take all three of them. For example, already we know this, we know this, we know that, we don't know stress. So stress over y is equal to m all over I. Stress is equal to m over I times y. So already to calculate the bending stress, remember I said this is your y bar. So we'll calculate the bending stresses at the extreme ends of the section, of the cross section. I'm gonna take an I section, for example. So your bending stress is always something like this. Okay, so what is the stress at the top? Therefore, if you're calculating stress at the top, that means you must use y upper for that cross section, for this cross section. This is the cross section. This is your I section as your cross section. So what is the stress at that top? So what is the applied moment at that top? You've calculated using your bending moment diagram. So you know what is the applied moment at that particular top, whether it's over the support or it's a settling moment or a hooking moment. You know that M. You can work, you know I, and you know Y. Y will be determined on whether what determines Y. Where are you calculating? Are you calculating the stress at the bottom, or are you calculating the stress at the top? So meaning we used the first two terms of that equation. We didn't use the E and the R. So if you can just stick to these guidelines, and you will never go wrong. And bending stresses, I think they are very straightforward. You can see as you approach the center of the section, the stresses are getting smaller and smaller and smaller. Hence, you're going to see some sections with an opening in the middle of the section, of the cross section. Think about now the bridge deck. Sorry. Then there's an opening there in the middle for services. So already we know the stresses. You work out the stresses, shear and bending stresses for that section, and then you work out can the remaining section handle the stresses around this area. That's designed for you. Can this one, the bottom one, handle the stresses at this point? Because you don't want to over stress your section. You don't want, because there are limits as well that you must think about, that you don't want the stresses to be more than whatever, and the limits are determined by this reinforcement that you have there. You can't stress the bars more than what the bars can handle. There are so many factors that you consider when you are doing this. You are analyzing, or you are preparing to go to the design. Hence, I always say to my students, design doesn't only start at when you're starting to. I'm designing now. The course is called design. There's a link between determining the loading, analysis and the profile that you choose, then it leads you to design. So if you've done your homework from the beginning in terms of how everything is going to tie together, then the design part of it becomes easy. So the most important stages are the initial stages, where now you need to remember the transportation. How is this section gonna be transported on site? I can't just, how is the site itself? How is the site? Can we have a crane on site and all that stuff? That all start with analysis. But anyway, we're not there. I sometimes get carried away. Please forgive me, guys. Okay, now there's a bending stress, or you can write this as a bending stress is equal to M over Z. I'm replacing that with M over Z. Why? What is Z? Z is your section modulus. Is your section modulus, where Z is equal to I over Y. So if it's easy for you to use this equation, use it, but it's the same as this. Z is a section modulus, modulus of elasticity, radius of curvature, applied moment, second moment of area, y lower or y upper. That determines the position of your second moment of area. This is your stress. It's as simple as that, guys. Determining bending stress is as simple as that. For example, if for example you have a beam, I'm gonna give a simple supported beam with a uniformly distributed load of 25 kilonewtons per meter. That is 5 meters. So we'll talk, maybe it's a rectangular section. I'm just giving you guys a simple, straightforward. It's 225 millimeters. Okay. You don't know that. You want to size the beam. I'm going to say you want to size the beam. Okay. I'm going to call that dimension B. The architecture has told you that you can have a beam of that depth. I don't mind, as long as it does not exceed that depth. Now you want to determine what must be the B dimension of that depth. I know the loading that the beam is subjected to. I know my spans is spanning from that end to that end. The architecture told me that 2 to 5 millimeter deep beam is fine, nothing more than that, because it's going to interfere with the looks of the building. So the question is now, how do you go about work out the dimensions of that beam? And let's make it interesting by saying that you are told that the maximum stresses, you can't stress the beam more than 6 newtons per millimeter squared. That's the maximum stress that the beam can take. So how do you go about determining that dimension B? So I know, first of all, let's work out. I know if it's simply supported like this, guys, there is no, and the load is spent over that is simple. M, that is the maximum positive moment. Remember, the moment is 0 there. The moment is 0 there. You want the moment in the what? In the middle. Okay, M is equal to WL squared, over 8. Please don't confuse this with fixed end moments. WL squared over 8. My W is 25, my length is 5 squared over 8. And that gives me an opportunity to look for a calculator. I'll pause the video just to look for the calculator. Please forgive me guys for that. Okay, so what is my maximum moment? 25 times 5 squared divided by 8, which is 78 13 kilonewton meter. That is the maximum moment. So stress. Remember this stress, you will be told whether the beam at the bottom at that point must not be stressed more than this, or at the top. The stresses at the bottom must not be more than this. What do we know? Okay, I'm gonna draw the bending moment diagram for you. There's your bending moment diagram. Because it's a UTL, so it's curved. This moment here is the 78,13 kilonewton meter. And there the moment is 0. There the moment is 0. So for a simple supported beam with a uniformly distributed load, your maximum moment in that beam is WL squared over 8. If it was a point load, it's PL over 4. It's PL over 4. Please don't confuse fixed end moments and the moments. Maximum positive moment for a point load that is acting at the center of the load, your center of the beam. The point load acting at the center of the beam there. If it's simple supported, PL over 4. If it's uniformly distributed load spanning over the entire span, the load is over the entire span, WL over 8. So what do you have now? We know this, we know the moment. We know the moment, the I value, but remember our I value is going to be in terms of B. So, sorry about that. In this case, my Y lower is equal to my Y upper, because it's a rectangular section, which is 2 to 5 over 2. And that gives me 112.5 millimeters. So, regardless of whether I'm asked to calculate the stresses at the top or stresses at the bottom, in this case, because Y lower and Y upper are equal, then I'm gonna be able to calculate this. Remember, I said stress is equal to M all over Z, or stress is equal to M over I. Sorry, I must make sure that I've got it right. Over I times what? Times Y. I said where Z is section modulus. Z, where Z is equal to I all over Y, and is in millimeters to the power 3, or Z for a rectangular section, or Z is equal to BD squared over 6. I hope I've got that formula right. It's BD squared over 6. So for me, instead of calculating I, instead of calculating I and Y's and all that stuff, I can go straight and calculate Z. But remember, my Z is going to be in terms of B. B is the dimension that I'm calculating, times D is 225 squared over 6. Then 225 squared divided by 6 gives me is 8437,5 B. That is my Z. So I've got my Z. I know my stress is 6. I know my M. So I can simply take this now and substitute there in that equation. Stress is 6. This one is 6, is given as 6 is equal to M. I know M. I've calculated M here as 78,13. 78,13 times 10 to the power 6. I am converting my M into Newton millimeters. Then I have here my Z. Z is 8437,5 B. Okay, now what is B? Take that side, take B that side, and then 6 will come there. So B is equal to 78,13 times 10 to the power 6 divided by 8437,5 times 6. Let's see if we're going to get a meaningful answer, because that's very important, guys. In terms of structures, you don't just accept the answer. The answer must be meaningful to you. 78.13 exponent 6 divided by 8437,5 times 6. Something is not right. To me, it doesn't make sense. To me, this answer doesn't make sense. So 8.13 times 10 raised to the power 10 raised to the power 6 divided by 8437,5 times 6. No, this answer doesn't make sense. 1543,31 millimeters. This answer doesn't make sense. Maybe there is something that I am doing wrong here, that I need to check. Or maybe my assumptions were completely wrong. I don't know what's happening. Let me just quickly check it. I see what I did wrong here, guys. What I did wrong here, guys, my assumption for the load of 25 kilonewton is too big, it's too much. Hence, I'm getting an answer that is meaningless. So, if you can just change that, I'm gonna reduce that to 3,35 kilonewtons per meter. I'm reducing that load to 3,35 kilonewtons per meter. So 3.35 times 5 squared divided by 8 gives me a moment of 3,35 times WL squared 5 squared over is giving me a moment of 10,47. Even that moment is high, but it's fine. Kilonewton meter, 10,47 kilonewton meter. Then I come over same exercises. The only thing that I'm going to change here is this value to 10,47. So 10.47. Hopefully this one is gonna give us a meaningful answer now. 10.47 times 10 to the power 6 divided by open bracket times 6. It's 206. It's 206.81 millimeter. Even this one it's a bit too much. You cannot have a beam. It's almost a square beam. This side, let's say, is 210. This one is 225. So even this one is too much. Maybe I need to, now that's where now you need to speak to the what, to you start negotiating with the architect. Now, can I get up to 250? Then I'm reducing that dimension, because this section is not a very economical section. It's wide, but it's not, it doesn't have the right depth. So I reduce that, and then I give it a little bit of depth, maybe to 150 to 250 millimeter diameter beam. So, but the concept, I think you've got the concept, guys. But the most important thing, guys, is to know how to work out the stresses, the bending stresses for the beam. So, and remember, sometimes you will be limited by the depth of the beam. Sometimes you will be limited by the stresses, or by both. The depth of the beam, you are told that you may not exceed a certain depth, and you're limited by the stresses, that the maximum stress that you can have on that beam, the bottom or top, depending on the type of the beam you're having, it must not exceed 6, for example, or it must not exceed 10. Then you're limited. You've got those boundaries that are limiting you as a designer. So meaning you must be able to try and be within those boundaries. I hope you enjoyed the video, guys. Thank you very much, guys. Thank you. I'm sorry for the disturbances that I was having. Even now there's a car that is stopping outside to fix some stuff at home. My apologies for that, but luckily I'm done for what I wanted to cover with you today. The next video I will be showing you how to calculate the shear stresses in the beam. Thank you very much, guys. Thank you.